It's a great honour for me to be here at this meeting talking about animal research. As Carl mentioned, the laboratory animal research is often the foundation of a lot of the concepts that we then go on to test in clinical research and the evidence that we then try to take into practice. The theme of this session, that my co-speakers and I have taken slightly different approaches to interpreting the idea of too much and too little medicine. So I am going to focus on this part of the development pipeline, too much laboratory research, and how that doesn't lead to enough medicine working in clinical research. So Cariadas stands for the collaborative approach to meta-analysis and review of animal data from experimental studies. And what we do is look systematically across the range of modelling from a range of different conditions. So we now have a database that has evidence from 19 different disorders, our systematic review, and collected in the context of systematic reviews, with over 7,000 studies and more than 200,000 animals. So if we think that generally preclinical studies are performed with the purpose of improving human health, then we perform systematic reviews and meta-analyses of these data to assess the quality and range of evidence that exists. We try to identify where we have knowledge gaps in a field. We assess for publication bias. We try to explain the discrepancies between the positive results that we often see in an animal study compared to the clinical trial results that we see. And we've also used systematic reviews of animal studies to inform the design of clinical trials. Now, the major fundamental differences when we look at the evidence that might exist in animals compared to clinical trials is that we have many more smaller animal studies compared to fewer but much larger clinical trials. I always underscore my talks with this slide a slide of correlation versus causation. You'll all be clear that the work that we do is observational. We're looking at already completed studies, so should be considered hypothesis generating rather than confirmatory. I'm hoping that in the next year that my correlation versus causation slide won't be something to do with Britain's left Europe and we don't have any funding to do any more research. So too much and too little medicine. So we got into this research with the hypothesis that in the life sciences, there are a number of perverse incentives, things like getting your work published, things like securing funding and academic promotion to produce lots of positive results with less attention paid to the validity of the results. I think in the use of animal disease models, there are additional pressures to reduce the number of animals that you use because of things like cost, time, ethics, feasibility, that results in many studies being of unknown power or being underpowered, and together these factors can combine to compromise the utility of animal models and I think contribute to translational failure. So there is a lot of information out there now. If we look at how many papers are published, it's more in a day than most people could read in a month. In 2013, 4,700 publications were added to PubMed every working day. So if you take just the animal studies, the in vivo studies, that's 350 publications a day, and 52 of those are in the neurosciences. So if you imagine that you're a panelist on a neuroscience grant awarding body, and you're trying to keep up to date with what's going on, what's in the literature, and you spent just 30 minutes reading each paper and did nothing else but just read papers for a year, you could only get through about 30% of the available evidence. So this is a huge amount of data that we're trying to consume. But I know most people aren't trying and keep up to date with everything. But even within a specific field, there's just a huge amount of data. So this is a review that was done 10 years ago now, where colleagues in Australia looked at all the different interventions that have been tested in models of stroke. There are over 1,000 interventions, 600 of these interventions tested in animal models of stroke. 374 were reported to be effective in these animal models. 100 were taken forward to be tested in clinical trials. And like I said, this was 10 years ago, so these numbers have invariably gone up substantially from when this review was done. But this number hasn't changed. Still, only one treatment, thrombolysis with TPA, is effective in clinical trials. And there's some other treatments that are effective that have never seen an animal. And this this data here is probably slightly disingenuous because the clinical trial wasn't initiated because TPA was shown to be effective in animals. It was initiated because of efficacy in myocardial infarction. So what's clear for animal data, at least for stroke, there's huge amounts of it. I think it's quite confusing. So we try to use systematic review to make sense of it. This is an example from a review that we did looking at therapeutic hypothermia. So for therapeutic hypothermia, there were 222 experiments that we identified that used over 3,000 animals. We've ranked each of these 222 experiments in order of increased efficacy with the 95% error bars here. And this grey bar behind the graph here is the overall global estimate of effect. So if you go to the published evidence, you can prove that hypothermia is either harmful or substantially beneficial. But I think investigating the sources behind this variation is what may be useful for translation, rather than taking this headline hypothermia as 44% effective at improving stroke. So I'm going to talk about two aspects in how you perform animal experiments that I think are actually they're low-hanging fruit in terms of how we can try and improve the translational failure that we see. I'm first going to talk about internal validity, so the strength of the cause-effect relationship in an experiment. Is the effect we see because drug X has caused an improvement in drug Y rather than other unknown sources of bias? And then I'm going to talk about reporting biases. So I said in Cariadas, we systematically review the use of interventions across different disease models. So here we've got evidence of the reporting of measures to reduce the risk of bias, randomization, whether the investigators blinded the assessment of outcome, whether they report a sample size calculation or conflict of interest statement across a range of different disorders: Alzheimer's disease, focal cerebral ischemia, glioma, Huntington's, intracerebral hemorrhage, EAE, which is a model of MS, myocardial infarction, and spinal cord injury. These are 2,600 different studies in total, and we can see across the board that most studies are at high risk of bias. They don't report measures to reduce the risk of bias across these different domains. And the impact of this is that when we do a meta-analysis and we stratify according to studies that do or don't report measures to reduce the risk of bias, we see that studies that don't report these measures tend to overstate treatment effects. So this is where the studies reported blinded assessment of outcome in models of stroke, Alzheimer's, multiple sclerosis, and Parkinson's. And we consistently see that these studies at high risk of bias report much larger treatment effects. But things are improving. When we stratify this by time, we see, at least for randomization, blinded assessment of outcome, conflicts of interest statements, people are generally starting to report these more than they did. However, we really do have an issue in terms of reporting how investigators decide how many animals they're going to include in their study. One of the major criticisms that we received with our work is that we look for reasons for translational failure where we know it's happened. So we know that in stroke, lots of drugs haven't worked. So when we've gone back, we found a reason. So what we decided to do was to say, okay, let's just randomly sample from PubMed. And we used a random number generator to create 2,000 PubMed IDs. We found from those 2,000, which were in vivo studies, about 560 odd that were in vivo studies. And then in this random sample from PubMed, we looked at the prevalence of reporting of measures to reduce the risk of bias. And it's not much better, to be honest. Randomization is at about 18%, less than 5% report blinded assessment of outcome, very few reported a sample size calculation, and about 10% reported a conflict of interest statement. And when we stratify this by year, we see that conflicts of interest statements are definitely much more common than they used to be, and there's an increase in randomization. But again, when you look at the y-axes, these levels are still very low. So then people say, well, that was a random sample. There's lots of junk in there. What if you look at high-quality journals? You know, these high impact factor journals are going to be the journals that report good quality science. So we said, okay, we'll look at whether there's a correlation between impact factor and the prevalence of reporting these measures to reduce the risk of bias. So on the x-axis here, we've split the data according to decile of impact factor. and looked at the prevalence. And actually for randomization, high quality journals are less likely to report randomization. It's a flat line for blinding, it's a flat line for sample size calculation, but high quality journals do report conflicts of interest statements. And then people say, yes, but what you really want to look at is high quality institutions. The best institutions are the ones who are going to produce the best quality research. So we said, okay, we'll have a look. We used the 2008 research assessment exercise and took the top 5 Russell Group universities. I've labelled them A to E, just so that no one refuses to give me a job in the future. And then looked at the reporting of measures to reduce the risk of bias, and it's no better. Randomization, it's about 15%, a bit higher for blinding, 10% report inclusion-exclusion criteria in their studies, and less than 5% report a sample size calculation. So if we compare these data sets just from, so when we looked at the top universities, we just looked at the in vivo studies that they published in 2009 and 10. So if we look at these 3 data sets in 2009 and 10 and just look at randomization. So the top 5 universities, less than 20%. Our systematic reviews in the Cariadas database, it's a bit better. But actually, you're more likely to find high quality publications by randomly sampling from PubMed. So I think there are a number of improvement strategies that are in place. I think people are becoming much more aware to this issue of reasons for translational failure and irreproducibility in preclinical research. So we have the ARRIVE guidelines, which are the animal research equivalent of CONSORT. We've got the LANDIS guidelines, which were developed by NIH in the States to look at transparency and improving transparency of the research that they fund. The Nature Publishing Group changed their editorial policy that now requires investigators or authors, when they submit an article, to explain how they chose the number of animals they used, whether they randomized, if they didn't, why they didn't, blinding, etc. We're also involved in a randomized controlled trial with a publisher where authors who submit in vivo studies are randomized to either be requested to complete the ARRIVE checklist or not, and then we will then assess whether completing these reporting guidelines actually leads to an improvement in the quality of reporting. I think there should be more emphasis in rigor in grant award rather than these big headline, big effect sizes. And I think as this information becomes much more available and there's much more evidence to show that these measures to reduce the risk of bias are important, then there should be CPD opportunities for scientists as well. So I'm now going to touch on reporting biases. So there are a number of different types of reporting bias that exist. Neutral negative studies are less likely to be published or might take much longer to be published. Selective outcome reporting, I think, is a real issue in animal studies. It's quite often that in an animal study you may look at lots and lots of different outcome measures in your experiment, but then only those outcome measures that show you a significant difference are the ones that are included in a publication. And then you also have selective analysis reporting, where lots of different tests may be used, and the test that gives you the answer that you want to present is what you include in your manuscript. I don't know if many of you follow the hashtag overly honest methods, but it's great. It's got all sorts of interesting things that people do in the lab that will put a smile on your face. So we looked at publication bias in reports of experimental stroke in our Cariadas data set. And we did this using a funnel plot, first of all. So we had 525 publications that we included in this analysis. And we see, so where there's no publication bias, you expect that precise studies will lie around the true effect. And then as you become less precise, you should have an equal distribution of both positive and negative studies. In our data set, we see a lack of imprecise negative studies. We statistically tested for this asymmetry using egg regression, and the regression line and its confidence intervals didn't go through the origin, so suggesting that there is publication bias in this data set. We also used trim and fill, so a technique that attempts to impute these theoretical missing studies and then readjust your overall effect, taking into account these theoretical missing studies. And in our data set, our overall effect reduced from 36% down to 26%. So in experimental stroke, at least, Trim and Field suggests that about 16% of experiments remain unpublished. The best estimate of the magnitude of this problem is that we're overstating treatment effects by about a third. And I think this is actually a gross underestimation of the real magnitude of this problem, because in that funnel plot, lots of the studies on the left-hand side, the negative studies, are experiments that are published alongside positive studies. So people might do dose-response experiments or time-to-treatment experiments. So lots of the negative studies are published alongside the positive studies. And actually only 2% of the publications reported no significant treatment effects. We've looked at, or looked for the presence and impact of publication bias in other disease models, so these models of MS and Alzheimer's disease, and see similar estimations of the problem. About 20% of experiments remain unpublished, and that when you try and correct for this, that we're overstating treatment effects by about a third. Interestingly, we've seen that we observe different patterns of publication bias depending on the field that you're looking at. So in experiments of disease models where you're looking for improvements of outcome, we observe, when we adjust for publication bias, that the true benefit is less. When we've looked at this in toxicology models where your outcome is harm, we see the opposite direction of publication bias, that actually there's more harm than is in the published literature. So improvement strategies, journals, I think should be journals of record. It should be clear what someone's actually done in their studies. So if they set out to assess outcome in assess improvement in lots of different outcomes, then all these outcomes should be included. I think in the 21st century, I think we should be thinking about different publication models. We have, the internet, it's easy to access information now rather than in print, like it used to be. So this issue of space, I don't think it's the same issue that it was before. I think we should encourage rapid publication rather than trying to go for these high impact journals. But of course, it's a cultural thing. It's the high impact journals that lead to getting your funding and promotion. So I think there should be at least some reflection on the impact of this culture on what it does more broadly in preclinical or in academia generally. So how can we increase the chances of translational success? Well, and I know I'm biased, I think systematically reviewing the data is a good start. I think where it's indicated, when you know where the knowledge gaps are, where there aren't data of sufficient quality, then further experiments that are informed by what's done before, I think would be useful. I think clinical trials should be designed where we know where evidence exists from the preclinical literature. And because of this increasing wealth of information, because we're publishing 350 publications a day, I think we do need to think about developing tools to allow us to rapidly consume this information. So whether it be text mining or machine learning or using different techniques to be able to access the level of information that we are privy to. So the key messages that I wanted to get across today is that in vivo studies, which don't report simple measures to reduce the risk of bias, tend to give larger treatment effects. Most in vivo studies do not report these simple measures to reduce the risk of bias. I think publication bias and selective outcome reporting bias are important and they're relevant. I don't think you can assume rigor, even in journals of impact. You can only find out these things, I think, by studying large numbers of studies and seeing these patterns. I think any experimental design can be subverted, but it's important to know how to recognise when this has happened. And with that, I thank you all for listening and my team back in Edinburgh.